In this video, we'll be covering the concept of the limit definition of the integral. First off, you'll notice that this definition here includes a limit, a summation of a function value times delta x. Now you'll notice down here that our delta x is b minus a divided by n. If you reference this value to previous examples of the Riemann sums, this is nothing more than the width of the intervals that we've chosen to work with. You'll also notice right here that xi is equal to a plus I delta x. This is specifically the formula that we use when considering right endpoints, because we'd start at the initial value. If we were on a number line, we'd start at a, and then we're going to go ahead and move delta x. So this is a plus 1 delta x. And then we're going to move a second delta x, a plus 2 delta x, and so on and so forth up until we reach the value of b. So you'll notice here that this xi is nothing more than the right endpoint in the interval. Okay, on the first interval here, it's when I is 1. On the second interval here, it's when I is 2, and so on and so forth. So these two formulas should make sense from previous interactions with Riemann sums. Now the rest of this information is this summation of I equals 1 to n of f of xi delta x. This is, we said, the width of every interval that we play with. F of xi, you should recall from the Riemann sum that this is the height or the length of any rectangle that we're playing with. So again, one more time, the Riemann sum is the addition of all the areas of rectangles in the problem. So this right here is the summation of n rectangles of height h and width w, such that w is delta x and h is f of xi. Now the last piece that we've added to this problem is that the limit as n goes to infinity. So by adding this limit, what we're really doing is we're forcing the number of these rectangles. So from a to b, this interval isn't changing, but what we're going to do is we're going to shrink every single one of these rectangles, smaller and smaller and smaller, so that we have an infinite number of rectangles slicing this entire interval from a to b. So that does mean that our delta x is going to change. It's going to change to this distance right here between these two little dashes. Or, more appropriately, it's going to change so that it is infinitesimally small cut between any one of these dashes. So this right here, if we recall from Riemann sums, is the best estimate for any area under the curve, because the number of rectangles that we're going to have, the more we have of those rectangles, the more accurate our estimation of the integral is, or the area under the curve is. So when I take the number of rectangles and send it off to infinity, I should have a perfect representation of the area under the curve. For instance, in this example right here, we are attempting to graph that one same exact function we've done in the past of y equals x squared. We're going to go from 0 to 4, and the concept, and again the concept of this is that we want to slice this into so many infinitesimally small rectangles that every single rectangle is a single line that goes from the x-axis to that function, that it has a width of nearly 0. Now keep in mind, a width of nearly 0 does not mean that it is of 0, and does not mean that by adding all these width zeros up, we have no area. So in the concept of this limit will analytically evaluate this summation such that this summation simplifies down to something of a function of n. So this is the concept of what we're going to be doing for each one of these examples. Again, the idea is we are simply slicing this region into an infinite number of width 0 or nearly width 0 rectangles.